Hi everybody, I am Sankareswari, Assistant Professor of Physics, V.V. Perumal College for Women, Virudhunagar. I am going to explain about the expansion of solids. So almost all bodies expand on heating. When a solid is heated, the expansion may take place in three different ways. If the expansion takes place in lengthwise, it is called as linear expansion. If the expansion is in aerial or superficial, then it is called as aerial expansion. If the expansion is in volume wise, then it is called as volume expansion. So different bodies expand to different extents for the same rise of temperature. So the property of linear expansion is denoted by a term called the coefficient of linear expansion or linear expansivity alpha. And the coefficient of linear expansion alpha is defined as the ratio of increase in length per unit rise of temperature. Likewise, the coefficient of aerial or superficial expansion beta is defined as the ratio of increase in area per unit rise of temperature. Similarly, the coefficient of volume expansion is defined as the ratio of increase in volume per unit rise of temperature. Now, let me explain how to determine the coefficient of linear expansion of a crystal by air wedge method. So, figure shows the experimental setup used for the air wedge method. Here, OA and OB are the two optically plane glass plates. The two glass plates are hinged at the point O. They are separated by a small distance T at the other end. A parallel beam of monochromatic light is allowed to fall on the glass plate OB after reflection at a glass plate G, which is inclined at an angle of 45 degrees. Now, part of the light gets reflected at the upper plate OB and a part of the light will be reflected by the lower plate OA. The two reflected beams will produce alternate bright and dark interference bands of equal thickness. The interference bands are viewed by the microscope M. Let T1 and T2 represent the thicknesses of the air film at two successive dark bands C and D respectively, and lambda is the wavelength of light used. Then 2T1 is equal to n lambda and 2T2 is equal to n plus 1 lambda, where n is an integer. So from equations 1 and 2, we can find T2 minus T1 is equal to lambda by 2. Let theta be the angle of the wedge and beta is the bandwidth. Then we can calculate theta is equal to T by L. And by comparing the equations, we can calculate T is equal to lambda L divided by 2 beta. And this is the experimental arrangement. Here OA is the base plate, OB is the cover plate. Both the glass plates are polished and optically plane. The plates are hinged or tied at O. The free end B of the upper plate rests on the pointed upper tip of the crystal. The lower end of the crystal rests on the projection of the base plate. A heater coil is wound on the crystal. A parallel beam of monochromatic light is made to fall vertically on the air wedge. The interference bands formed are observed through the microscope M. Initially, the crystal is kept at room temperature theta 1. At the room temperature, the bandwidth beta 1 of the interference bands is measured and it is given by T1 is equal to lambda L divided by 2 beta 1, where T1 represents the thickness of the air wedge at B and L is the distance between the hinge O and the point of support B. Now, the crystal is heated to the temperature theta 2 by passing some current through the heater coil. Now the rod will expand. So the thickness of the air wedge increases and the bandwidth decreases. The new bandwidth beta 2 is measured. So now T2 is equal to lambda L divided by 2 beta 2. T2 represents the final thickness of the air wedge. Now we can calculate the increase in length of the crystal by measuring the difference between T2 and T1. Therefore, E is equal to T2 minus T1, that is equal to lambda L by 2 into 1 by beta 2 minus 1 by beta 1. Here capital L represents the original length of the crystal. Now we can calculate the coefficient of the linear expansion of crystal alpha by finding the ratio of increase in length divided by original length into rise of temperature. Therefore, we can find alpha is equal to lambda L by 2 into 1 by beta 2 minus 1 by beta 1 divided by capital L into theta 2 minus theta 1. Thus, we can calculate the linear expansivity of the crystal. Next, expansion of anisotrophic solids. If a crystal is anisotropy, the properties are different in different directions. Then its thermal expansion is different in different directions. If we consider a cubic crystal and we heat the crystal, different sides of the crystal will expand in different level and therefore its sides will be unequal. The three mutually perpendicular directions in a crystal are called principal axes of dilation. If a cube is cut with its sides parallel to these directions and heated, the dihedral angle remains unchanged. The linear expansivity along these three directions are called the principal coefficients of expansion and they are represented by alpha 1, alpha 2 and alpha 3. So now we have to consider a cube and the side of the cube is represented by L0 at 0 degrees Celsius. Now the cube is cut with its edges parallel to the principal dilation axis. When it is heated to theta degrees Celsius, it becomes a rectangular parallelepiped. Its edges are given by L0 into 1 plus alpha 1 theta, L0 into 1 plus alpha 2 theta and L0 into 1 plus alpha 3 theta. Now volume of cube at theta degrees Celsius is V is equal to L0 cube into 1 plus alpha 1 theta into 1 plus alpha 2 theta into 1 plus alpha 3 theta. L0 cube can be written as V0. So V is equal to V0 into 1 plus alpha 1 plus alpha 2 plus alpha 3 into theta. Now we can neglect the products alpha 1, alpha 2, alpha 2, alpha 3, alpha 3, alpha 1. So now V0 is nothing but the original volume of the crystal at 0 degrees Celsius. Therefore, the coefficient of cubical expansion gamma is given by gamma is equal to V minus V0 divided by V0 into theta. So we can also write gamma is equal to alpha 1 plus alpha 2 plus alpha 3. Next, solids of low expansivity and their uses. Silica has very low expansivity, and from the graph which is drawn between the linear expansion and the temperature, we can find that it is a straight line from room temperature up to 1300 Kelvin. So silica vessels can be heated to a very high temperatures and cooled suddenly without any fear of breakage. When quartz fused and re-solidified into non-crystalline state, it is called as silica glass and it is used for making thermometer tubes and large telescope mirrors. Next, invar is an alloy of nickel and steel, that is it is a mixture of 36% of nickel and 64% of steel, and invar is used for making survey metal tabs of constant length, precision clocks and watches. Invar is an alloy similar to invar with certain proportion of chromium added to it. Used in the construction of it is used in the construction of hairsprings of balance wheels of watches and chronometers. Next one, thermostat. So thermostat is a device by means of which the temperature of a bath or any closed space it can be maintained at any desired temperature for a long time. If the temperature of the body exceeds the desired value, it automatically cuts off the heat supply. If the temperature falls below the desired level, heat is supplied immediately. Different types of thermostat are bimetallic thermostat, liquid thermostat, thermometer types of thermostat and vapor pressure thermostat. Figure shows the bimetallic thermostat. It consists of a bimetallic strip AB, which is obtained by welding brass and inward strips together, and H is a heating coil. E is an electric heater. When contact is made between C and D, current flows through the heater coil H. The temperature in the electric heater increases. Now the brass part of the bimetallic strip expands more than the inward part. Therefore, due to unequal expansion, the bimetallic strip bends upwards. This breaks the contact between C and D. Then the current through the circuit will stop. When the temperature of the enclosure falls below the desired limit, the bimetallic strip cools and becomes straight. Contact is again made between C and D, and heating of the enclosure is resumed. Thank you.